Today we are going to be solving rate problems, and we are going to set up a system of equations to solve these problems. So the first problem is similar to numbers 6 and 10 on today's assignment. Again, it comes from a handout called handout number 1, and I will be doing numbers 1, 2, and 3, the large problems, and then the smaller problems down towards the lower left of the page, numbers 6 and 10. They're numbered, are similar to number 1. So let's take a look at it. It talks about a car, and it leaves Hartford traveling north at 56 kilometers an hour. And so what's happening here, if I drew a picture of what's going on, we've got this car, and here's Hartford, and it's traveling north at 56 kilometers an hour. And then later on, about, what was it say, an hour later, a second car leaves Hartford. So it leaves the same town, and it travels north as well, but it goes a little faster, and they say, when will the second car overtake the first? So what that tells us, the second car overtakes the first, that means they've gone the same distance. That means this distance right here, this distance is equal. The two cars will have traveled the same distance when one car overtakes the first. And that's critical here. And actually, they give you that as a hint. So overtakes the first, that means they've gone the same distance. So we're going to use that concept when we are solving this. So what we've got with these problems is a formula, and that formula goes this way. Distance equals rate times by time. And the way I like to set these up, these distance equals rate times times problems, is in a chart form. And so let's do this. Let's go ahead and write down our two scenarios. So first one, we have this first car. And we'll call this first car that goes 56 kilometers an hour. Let's call this our slow car, because he's just going a little slower than the other. And then the one that's going 84, let's call this one our fast car. And so let's write down slow car, and so we know that's the slow car, and then we also have an equation for our fast car. Kind of like when I set up a problem and I talk about the quantity equation and the value equation, same sort of thing. So we'll write our distance part right here, and then we've got our equal sign here, and then rate times by time. So let's go ahead and fill in some of the parts for our equation. So I'll go ahead and draw a little chart here as well. And I think this just helps us figure out, gives us some cells to put different things in. And I think that's what's helpful with setting up a chart like this. So first part here, let's take a look at, again, their distances. Now, again, as I was saying, those two distances are going to be the exact same. Do we know the distance? No. And actually, that's what they're asking for. They're asking for how far. So they want to know the distance. So let's go ahead and put a d in place of distance. So we don't know the distances, but we do know they will be the same distance. So that's why I'm using the same variable. Now their rates are different. So we said the slow car goes at 56 kilometers an hour. So let's put that time in there, or that rate in there, 56. The fast car goes 84. So let's put 84 in place of the fast car's rate. And now the times are different. And so there's a couple ways we can set it up. Let's say the first car here, the one that traveled first that's going slower, let's say his time is t hours. We don't know how long, so I'm just using a variable to represent it. And t makes sense because it's the time. Now the fast car leaves 1 hour later. So is he traveling longer or shorter? Well, since he's going faster and eventually he catches up and he left an hour later, that means it's minus 1 from the time that the slow car traveled. So the slow car traveled t hours. So we need to take 1 away from the time that the slow car traveled, and that will give us the time that the fast car traveled. So now we have our equations. See, this equation is d equals 56t. This equation is d equals 84 times by, and then I need to put this in parentheses because t minus 1 is one number. So let's go ahead and rewrite our equations here. D equals 56t, and the other one is D equals 84 multiplied by t minus 1. So let's go ahead and use that substitution method. It makes the most sense since D equals both equations. So we're going to set the two expressions equal to each other. So we can write down 56t equals, and then this one here, let's go ahead and multiply this stuff out. 84t minus 84. So I just used the distributive property there. And we can go ahead and collect some like terms. However, there's no terms on either side that we can collect, so we've got to use opposite operations in this case. So I'll subtract this 84t from both sides. Now, be careful when you do this subtraction. Remember, I've got the bigger numbers on the bottom, so when I do that subtraction, I actually have to move some terms around here. I'm going to put the 84 on top just off to the side, and then 56 on the bottom, do that subtraction this way. This shows that I need to borrow from that 8, change it to a 7, and I end up with 28. And so I've got 28t equals, and this is a negative 28t because there's more negatives than positives, equals negative 84. So from this point, all I have to do is one operation. I just have to divide by negative 28, and we'll have our answer. So 28. Now let's see if it goes in there. Well, we go ahead and do that division now. I'm thinking that can't be something too much bigger. Let's try going with a 3. So off to the side you might do 28 times by 3 and see if that makes 84. So we go ahead and do that work. It makes a 4 at the end, which is a good promising sign. And that makes 6 plus 2 does make 84. So yes, that's the answer. T is equal to 3. But they want to know the distance, how far from. So how do we find the distance? We know time. Distance equals rate times time. So let's go ahead and take that 3 and let's substitute it in for time right there. It doesn't matter which one you put it in for. Either one's going to give you the same answer. So D equals 56 times by 3. Multiply the 3 and the 6, you get 18. Carry a 1. 3 and 5 make 15, plus 1 makes 16. So 168 kilometers is the distance that second car and the first car traveled before the second car ended up overtaking the first. Well, we got another problem here. This one here, about the canoeist paddling 4 hours with a current to a campsite and then end up going a different direction. This one is similar to numbers 8 and 12 on the handout number 1, which will be the homework problems you're assigned. However, the difference between this problem and numbers 8 and 12 is that this one deals with water and the other deals with going through the air, flying through the air. And so, but they're pretty much set up the same. They get the same concept in there. So let's see what's happening here. A canoeist paddled 4 hours with a 6 km/h current. So they're going one direction, and they're going a little bit faster because the current is pushing them. So here's the boat. The boat is going, or the canoe is going this way, and the current is going this way. So we'll say the current here. And so they're both going together that way. But then the return trip, the boat is going back this way, but the current is still going that same direction. So this is the return trip, RT for return trip. So we're going to use this concept of when you're going with the current's pushing you. When you're going against the current, well, that means it's going against us. We're going to use that concept as we are solving this. So again, it's a distance equals rate times time. So we're going to set up our two parts. We've got with current, and then we also end up going against that current. Just like on the last problem, we had the slow car and the fast car. And so I'm going to make my chart here. And we've got our distance. So this is the distance equals, and then we've got our rate times by time. And so draw our little parts And let's read off what it says. So we've got the return trip. Let's think about this. If we are returning, is that trip going to be the same or different? Well, if it's a return trip, that tells us it's going to be the same distance. We don't know what that distance is. They don't tell us. Sometimes they do tell us the distances on these problems, but this one they don't. But since they are the same, just like the last problem, we're going to call both of the distances d. We don't know what they are, but we know they're the same. So with the current, it says that this person, this canoeist, paddled for 4 hours with a 6 km/h current. So 4 hours goes in the time. This time we know the time. They tell us it's 4 hours. Now the difference is the rate. There's two components of the rate. We've got the rate at which the canoeist is paddling, so that's r, we'll say. But then we also have the rate of the current. So the current is pushing us. So this is the rate of the current, and they tell us this is 6. So let's go ahead and put plus 6. So the rate of the current, but we also have the canoeist paddling. So we don't know how fast this canoeist is paddling. So we're going to say the canoeist's rate is r. And we also have a 6 km/h current, so it's pushing us. Now going against the current, it took 10 hours. So it took longer because we were going slower. We had the same rate. The canoeist was still paddling the same, but we were going against the current. So against means minus. So that's the big thing. Minus means that when you're going against the current. With the current, that's why it was a plus. But now we're ready to set up our two equations. And that first one goes this way. We've got d equals, and then it's going to be r plus 6 in parentheses, and then times by 4. The other one's going to be d equals r minus 6 times by 10. So when we set this one up, I'll go ahead and take this whole expression right here, and I'm going to substitute it in for this d. So I'm going to go ahead and multiply this stuff out. It's 4r plus 24, so I use the distributive property. And on this side, I'll do the same, 10r minus 60. And so we go ahead and do some opposite operations. So here I'm going to subtract 4r from both sides. And then I'll also add this 60 to both sides. And so from there, I end up with an 84 equals 6r. All you do there is divide by 6, and you've got your answer. So 14 kilometers per hour. It was the rate. That's the rate in still water. Well, one more problem here, and this one is very similar. We've got the same sort of thing, and this one's very similar to the last problem that we have. Here we've got a headwind and with the wind. So we're going to write down headwind, and headwind means that we are going against the wind. A tailwind is with the wind. So those are the two components, just like with the current and against the current. And then we'll go ahead and set up our equation. We have d equals r times by t. And so with this problem, we end up with the distances. It says an airplane took 2 hours to fly 600 kilometers against a headwind. And so 600, this time we know the distance. It took 2 hours, and we're going against. Against means minus. So we've got r minus w. We'll say the headwind is w. We'll say that's what this is. Now, since we're going against the wind, that's why it is a minus. Now, with the wind, so with the wind, now with means that we are adding that term. It took less time. See, it only took an hour and 2/3 to go that full 600 kilometers. And so when we set this one up, we are going to end up writing it as 600 equals, and then we have 2, or r minus w first, times by 2. And then we also have this other one, 600 equals r plus w times by 1 and 2/3. And so from this point, we are going to use an opposite operation to actually cancel out these terms. And I'll show you how to do that in part number 2. So we'll have to finish this problem in part number 2 due to the fact that I've ran out of my 15 minutes. So check part 2 for the conclusion of number 3.